Thank you, sir, for such a warm welcome. First of all, I will share the screen. So, is my screen visible to all of you?
Yes, 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 yes.
Okay. So, well, today's lecture uh, is about well, we all know about square root of 2, and we all might know the proof of him. But there is a different proof. And let me tell you a story behind this. Sometimes my student asks me, sir, why different proofs are necessary, or are they necessary to learn different proofs? So I told them that yes, it is necessary because they give us different perspective. So when I learned the proof for that square root 2 is irrational, so what I was told, so I will start. And the main aim is not to understand the proof, but my aim is you that what different proofs gives us. So that's my first aim to tell you that in mathematics, what different proofs gives us. And the second is it's a nice example how to extend the proofs. Mostly you will find that lots of theorems are just the extensions of some standard theorems. For example, suppose if you all know fundamental theorem of calculus, and that is integration a to b fx dx is equal to f of capital F of b minus capital F of a, where f is anti-derivative. Now, if you extend this theorem in two dimensions, you will get Green's theorem. And the idea is very simple, that this integration depends upon the endpoints. So in Green theorems, this endpoints replaced with the boundary. So in mathematics, these two ideas are very important. That's what I wanted to explain you with the help of these examples, and you will find a lot of examples regarding this. Also, there is Rolle's theorem. You all might be aware of that. If not, then it's okay. And its extension is mean value theorem. So that's the idea. That's the main two aim I want to give you. So I'm going to start my lecture. Now, firstly, I want to give the definition, starting with the definition. Okay, so my first definition is Q, which is the set of rational numbers, and it is defined as P by Q, such that P and Q are integers. They are integers, and Q should be non-zero, otherwise it will not be defined. So we all know that this is the definition of rational numbers. Now, the real numbers, the set of all real numbers, is the union of rational numbers and the irrational numbers. So, what we want to prove is that square root 2 is irrational. Okay. So, first I want to give you the proof that we almost all of have heard and might know. So, we suppose let square root 2 is equal to p upon q. Then we square both sides. That will implies 2 is equal to p square upon q square. Okay. Here we assume P and Q are co-prime. There is a reason I'm giving you this proof. Just you can think like it a reminder, but there is a motive behind it. I will come to that later. So that will be 2p square is equal to, sorry, here it will come 2q square is equal to p square, right? Cross multiplying, right? Now that will implies 2 divides p square. Okay. And the next thing that will imply is 2 divides p. Now, to come from here to here, we use a theorem that if p is a prime, so I already used p. So suppose if say t, I'm using t, is prime and t divides ab, the product of two numbers, that will implies either t divides a or t divides b. Okay. So that is the theorem we need here. You all learned this theorem in uh, number theory, and also this when you extend these prime numbers definition in the group theory, these definitions play a very important role. So now that will implies p is equal to 2m. So we put the value of p in this equation. So we will get 2q square is equal to 4n square, and that will cancel out to 2, and we will have 2 divides q square. Okay. So again using this theorem, so that will implies 2 divides q, and we will have 2 as a common factor, as a common factor, which is a contradiction because we assume that p and q are co-prime, basically not any common factor other than 1. That's what we assume. So co-prime means they only have one common factor, that is 1. But here we come at 2 as a common factor. So that gives us a contradiction. So therefore, square root 2 is irrational. Okay. Now, if I ask you, what are the results we used? So look carefully. You need to be aware of what is the definition of a prime. You need to be aware of a definition of divides, what divides mean. You need to be aware that what is the meaning of common factor. So you need all these things. That is prime, factor, and divisible. And you all study all these things in a number theorem. Now, another thing is that if you want to extend this theorem, suppose you want more further results, so you can extend it as that square root of a prime is irrational. Okay, that you can do because instead of there is nothing special about 2, you use the property of a prime number. Okay, so instead of 2, you can take any prime, and that's the extension you can do. But what about others extension? What about 2 raised to power 1 by 3? Can you do that or no? Maybe you can, maybe no. We don't know. What about 2 raised to power 1 by 4? Or what about 6 raised to power square root of 6? Because 6 is not a prime. So that's the limitation we have in this proof. We need a lot of definitions, and when we try to extend it, we faced a lot of problems. Now let's look at a new proof, calculus proof. I call it calculus proof of square root 2 is irrational. Okay, so now you have the idea what are where we are going. So you don't need many things about calculus. All you need is that limit uh, r raised to power n, where is equal to 0 and goes to infinity, where 0 is, you can say, mod r is less than. Most of you know that if you have a sequence r raised to power n, that will go to 0 if the modulus of that number is less than 1. And if you don't know that, that's okay, because there is another thing you definitely know. It's nothing but the geometric sequence. Okay, and you can treat it like a geometric sequence. That's the thing. Now, again, I will tell you that you most of you know this result, but when we use this result, we use in a different way in our proof. So that I will explain when I will reach at that point. Okay, so we will use this. So firstly, all of you know the greatest integer function. That is also defined in the 11th, 12th class. Well, what is that? Suppose let x belongs to R, then uh, n is the maximum of all those, say, m belongs to integer such that m are less than equal to x. So it is the largest integer of all those integers which are less than x. So that is, suppose this is your x, then there are lots of integers. There can be many integers. Suppose 0 is here, 1 is here, 2 is here, 3 is here. So there are many integers which are less than x. So the greatest integer function gives us the maximum of all those integers. Okay. So if you go by this definition, then uh, you will not face problem in finding the greatest integer value of the negative numbers. And that's why you will understand why we call it a greatest integer function, because it is the greatest integers among those integers who are less than x. Okay. Now, if I ask you what is the greatest integer of square root of 2, well, we all know the value of the square root is approximately 1 point something. We are not 1.141, you can say. I'm not, maybe I forgot, but doesn't matter. We don't need that. But we all know that the square root of 2, the greatest integer value of square root of 2 is 1. Okay, that's what we know. So what we consider is, suppose our r, we consider our r is square root of 2 minus 1. Well, what will this gives us? That firstly, 0 is less than equal to r less than 1. There is a reason I'm putting equal to here, and I will again come to that later in this proof. But keep noticing these things. Now, firstly, what is R1? Well, R1 is square root of R raised to power 1, which is square root of minus 1, square root of 2 minus 1. What is R2? Well, that is R square, and that gives us a square root of 2 minus 1 whole square, which we can all open. So that will give us 2 plus 1 minus 2 root. Okay, so that is 3 minus 2 root. Okay, that's okay. R3, which is R cube. Well, there are two ways to find out R cube. You can root 2 minus 1 cube. You can open the formula with the help of a binomial theorem or simple calculation. And there is also another way, that 3 minus 2 root 2, which is the square of this number, multiplied it by square root of 2 minus 1. Well, that will give us 3 square root 2 minus 3 minus 2, and square root 2 into square root 2 will give us 2, so that will be 4 plus 2 root 2, and that is 5 root 2 minus 7. Okay, now if I want you to ask what is R4, well, that will be R raised to power 4 and square root 2 minus 1 raised to power 4, and so on. So Rn, which is R to power n, so square root of 2 minus 1 raised to power. Okay, that's okay. Now, another thing in maths, we always look for a pattern. Okay, so now look at the first term. Well, we have square root 2, we have square root 2 here, we have square root 2 here. The coefficient is 1 here, the coefficient is 2 here, the coefficient is 5 here. So what is common between 1 to 1 minus 2? Sorry, minus 2 coefficient is there, 5 is here. What is common between all these three numbers? The thing is, they all are integers. Now look the second term, that is minus 1, 3, minus 7. They are also integers. So what I can write is that the nth term will be of the form an square root 2 plus bn, where an comma bn belongs to integer. Okay, I hope everything is clear till now. If anyone have any doubt, they can ask. Okay, so now we have a sequence of the form an square root 2 plus bn, which is our sequence Rn, and that sequence is going to 0 because I already told you that power r is square root 2 minus 1, which is less than 1 and greater than equal to 0. Okay, now suppose square root 2 is rational. So we assume that square root 2 is rational. What does that mean? That means square root 2 is p upon q. Okay. Now in the previous proof, I assume p and q are co-primes, but here I am not assuming that they are co-primes. I'm just saying that it is of the form p and q, where q is not equal to 0. So basically, you don't know that what is the meaning of co-prime. So forget about that. So let us put that value here. So what we will get is Rn is An P upon Q plus Bn. Okay. Now if you take the LCM, so that is An P plus Bn into Q. Okay. Now An is an integer, P is also an integer, Bn is also an integer, Q is. They all are integers. So basically that is equal to Cn upon Q. Okay. So that is our Rn, which is Cn upon Q. Rn is Cn upon Q, where Cn belongs to. Okay. Now the magic of the calculus happens. So first, if I ask you using this limit n tends to infinity Rn is equal to 0. Using these two, we will prove that Rn is equal to 0 for some n greater than equal to capital. We can easily prove this. So again, there are two proofs. One is mathematically, but I want to explain it to you geometrically. So firstly, understand what does that mean. Uh, Suppose this is your real line R. Now, if I ask you where is 1 upon q, you will say somewhere there, here, 1 upon q will be here. 0 can be written as 0 upon q. Minus 1 by q will be here. So 2 by q will be here somewhere. Minus 2q by q will be here. 3 by q will be here. And minus 3 by q will be. Okay. So all the numbers means there will be no number lies inside this whose uh, numerator is q. Okay. So now what we have is Rn is Cn upon q. So we can take our epsilon if you know the definition. Otherwise, if you know the geometric meaning of a sequence converging to 0, it means after a stage, no matter how small interval you take, all the terms lies between this interval. Okay, that's the geometrical meaning, but we are going mathematically. So what we do is let epsilon is equal to 1 upon q, which is greater than 0. Then there exists capital N belongs to natural number such that for all n greater than equal to n, our term r raised to power Rn mod is less than 1 upon q. Now, what does that mean? Well, that means Cn upon q mod is less than 1 by q. Well, what does that mean? Well, that means Cn upon q is nothing but 0 upon q, because there is only one number. There is only one number in this interval which is of the form Cn upon q, that is 0 upon q. So what does that mean? That means Cn is equal to 0. Okay. So what does that imply? Well, we have Rn, which is square root 2 minus 1 raised to power n. And basically, I'm taking n is greater than equal to n. And that is equal to Cn upon q, which is nothing but 0. Now, any number raised to power n is 0. That means square root 2 minus 1 is equal to 0. Well, that will imply square root 2 is equal to 1. But we all know that is not true. That is not true. Not true. So therefore, square root 2 is irrational. Okay. So there is a from writing this not true. There is a technical mathematical technicality that you have to prove why square root 2 is not equal to 1, because you have, if you square it, you will get 2, but if you square the 1, you will get 1. That's a mathematical technicality, but we will go for that later part. So I hope you are clear with the that square root with the proof square root 2 is irrational. Now, in the proof, you don't know what is the factor, but you're still able to prove that. You don't know what are prime numbers, you're still able to prove. For the division part, you need the division, but you didn't need any divisible property here. You just, but for the definition part, you use that. Okay. Now, that's the one part. Now, what does it tell us? Now, why this proof is important. Now, if you want to extend the proof, now we want to extend the proof. So firstly, see what are the candidates here. So we write 2 raised to power 1 by 2. So there are two numbers. So we have to see, are these numbers playing any role or no? So suppose first we see this number and we replace it with n. Take any number. Obviously, we are taking the square root, so we are taking natural numbers. So square root of n we will consider. And we will go with the same technique. So firstly, we will assign a is the greatest integer value of this square root of n. And we consider the number square root of n minus a. Okay, a is the greatest integer of n, and we consider our r is equal to square root of n minus a. Now, this value is less than 1 and again greater than equal to 0. Now, in the previous part, you all know that square root 2 is not equal to 1. So that is obvious because we know a lot about these two numbers. But in this, we don't know. Maybe square root of n is equal to a. We have an example. So suppose square root of 4 we are talking about. That is equal to 2. And if you take the greatest integer of that number, that will again be 2. Okay. So that's why I'm taking here equal. Now, suppose take the R1. Again, that will be square root of n minus a. R2, well, square of that, square root of n minus a whole square. And that will give us n plus a square minus 2a square root of n. Now, if you take the R3, that will be square root of n minus a whole cube. And that will come out to be, if you again do some calculation, I'm writing the last result, but you can fill in the details. That is n plus 3a square, square root of n minus na minus a cube minus 2an. But that is not the important part. Important part is, again, these are integers because n is an integer, a is an integer. So they all are integers. So what we get is Rn is again of the form an square root of n plus bn. Okay. So again we will assume square root of n is rational. So square root of n will give us p upon q. This implies where p and q are integers and q is non-zero. Q non-zero and p comma q belongs to integers. So what we will get is r of n is an p upon q plus bn. And simply following the trick, you can take the LCM q a and p plus b and q, which is again cn upon q. So following the same trick, now you know there is no role played by 2 there. So therefore, Rn is equal to 0 for all n greater than equal to n. Capital N here for, I can call it k because I already used n here. So for some k belongs to natural. And that will imply my r, which I taken square root of capital N minus a is equal to 0. So that will imply square root of n will be equal to a. Okay. Now, eh, coming back to here, we don't know about n anything, so we can't say this is not true. But we can say if square root of n is not an integer, Or in this way, you can say that if square root of n is rational, then it is integer. So we have only two options. One option is square root of n is either integer or irrational. Okay, so if square root of n is not an integer, then it is irrational. So let's take an example for that. Suppose I want to know that what about square root of 6. Well, we know it is not an integer because you can see that 2 square is equal to 4 and 3 square is equal to 9. And if you square this number, you will get 6, which lies between 4 and 9. So 4 is somewhere here, 9 is here. So the square of that will be 2 and 3. So 3 square is 9, 2 square is 4, and 6 lies here. So the square root of 6 must lie between 2 and 3. Okay, so that's why this number is not an integer because there are no integers between 2 and 3. So square root 6 does not belongs to integer, therefore irrational. Now that solves one problem of ours. Now the another parameter is, I hope till now everything is clear. If someone has any doubt, you can ask.
We may give 30
Because
seconds time.
what's it?
We give 30 seconds time if any doubts are there.
Okay.
Okay, no questions. You can go ahead.
Okay. Now again, remember that we are always going to repeat the trick. So I'm here trying to explain how to extend the things. Now the another parameter we can uh, another parameter we can look. So we have 2 raised to power 1 by 2. The another parameter is this 2. So what we do is first, don't try to generalize as fast as possible. Look at concrete example. So what we do is we will see 2 raised to power 1 by 3, and can we apply the trick or no? Okay, then we will do it step by step. So if you will get familiar with the trick, you know that there will be no problem. So let's see this. Uh, so again, we have the number is 2 raised to power 1 by 3, and we will take our a is the greatest integer value of this. Again, the idea is 2 raised to power 1 by 3 minus a is less than 1, and that is greater than equal to 0. So our R1 will be 2 raised to power 1 by 3 minus a. R2 is equal to 2 raised to power 1 by 3 minus a whole square. Now, if you open it, that will give you 2 raised to power 2 by 3 plus a square minus 2a into 2 raised to power 1 by 3. Now, if I ask you what about R3, well, what you can do is 2 raised to power 1 by 3 minus a whole cube. And if you open that, you will get the cube of it, that is 2 minus a cube, because the cube of this number is 2 minus 3a 2 raised to power 2 by 3 plus 3a square into 2 raised to power 1 by 3. Now, if you look at this, this is an integer. Minus 3a is also an integer. Plus 3a square is also an integer. They all are integers. This also. But instead of two numbers, we are getting three numbers, like 2 raised to power 1 by 3, 2 raised to power 2 by 3, and some constants. Okay. So what we can write is Rn must be of the form. Remember that whenever we cube this number, this became an integer. So if you 2 raised to power 1 by 3, if you do the power 4, what will that becomes? It's 2 raised to power 1 by 3 cube into 2 raised to power 1 by 3. So that will be again an integer. That will be 2 into 2 raised to power 1 by 3. Okay. So that's why I'm writing Rn as an 2 raised to power 2 by 3 plus Bn 2 raised to power 1 by 3 and plus में Cn where An, Bn, Cn belongs to integers. Okay. Now again, what is the trick? We will assume 2 raised to power 1 by 3 is rational. So remember that while extending, we are doing nothing new, just repeating the trick. So 2 raised to power 1 by 3 is P upon Q. And if you put these values, what will Rn will get? An, that is the square of that number. So that will be P square by Q square plus Bn, P upon Q plus Cn. And instead of taking the LCM Q, here we take the LCM Q square. That is An P square plus Bn PQ plus Cn Q square. And again, that will become an integer. That term will become an integer. And we will reach dn upon Q square. And again, because Rn is going to 0, so therefore our R, which is 2 raised to power 1 by 3 minus A, will be 0 using the same technique. Hence, therefore, 2 raised to power 1 by 3 is equal to A. Again, we will say that 2 raised to power 1 by 3 is equal to A. So if 2 raised to power 1 by 3 is not an integer, does not belongs to an integer, then it is irrational. Or what other thing can you say? If 2 by 3 belongs to rational numbers, then it is integer. They are both the same thing. Okay. Because real numbers are either rationals or irrational. So if it is rational, then it is an integer. If it is not rational, then it will be irrational. So that's another way of saying the same thing. And that will tell that if it is not an integer, then it is an irrational. So that's also solved. So now to extend it further, that's the last extension I want to do. 2 raised to power 1 by n, because that will open up an interesting part again. So 2 raised to power 1 by n, if we are talking. So instead of taking 3, I am taking n. Okay. Now again, the trick is same. Take A is the greatest integer value of 2 raised to power 1 by n. Okay. Now here I want to use a different symbol. Instead of writing 2 raised to power 1 by n, I will write it as x, small x. There is a reason, and you will see that why I'm doing it. So I'm considering x minus a. Okay, x is nothing but 2 raised to power 1. So our R1 is x minus a, and R2 is equal to x minus a whole square. So that calculation is easy. That's why I use the x term. And there is also another reason for that. We will come to that. So x square minus, plus a square minus 2ax. Okay. Now if I take R3, that will be x minus a cube. And you all know the formula of a minus b whole cube. So x cube, I will write it firstly, minus a cube minus 3x square a plus 3a square x. Okay. So if you go down further, I want to stop at r raised to power n. Why I want to stop at r raised to power n? The reason is x minus a raised to power n is the first term we will get is x power n, and then plus the second term in this we will get mc1 x raised to power m minus 1 into minus a raised to power minus a, and so on. Okay, the last term will be minus a raised to power n. Okay, now what's so special about that? The value x raised to power n. Well, what is x? Well, 2 raised to power 1 by n. So if you take x to the power n, that will become 2. So that's why this become an integer. So that will be 2 plus some coefficient. So I will call it am minus 1 x raised to power uh, m. So we are here. So Rm is an equation. Now, so what I can write is Rn. Rn is nothing but is of this form am minus 1 x raised to power m minus 1 plus am minus 2 x raised to power m minus 2 and so on plus a1x plus a0. Remember that all these AIs belongs to integer from 1 0 less than equal to I less than equal to m. Now again the trick is same. We assume x is rational and x is equal to p upon q, and then Rn will be you can say bn upon q raised to power m minus 1, and you can apply the same thing. So far what we have is square root of what we get is 2 raised to power 1 by n. If not integer, then it is irrational. Okay.
Krishnan,
Yes. Yes.
I will ask one question to audience.
Yes.
Yeah, why it is q power m minus 1 k? By
Why it is
looking the
q?
pattern, yeah, not you. I'm just asking the audience.
Okay.
Participants, can you say that why it is q? By looking the till now observations, the pattern, can you tell me why it is m minus 1? Yeah, Aridas, go ahead.
Sir, because that if we are taking the if we are taking that x equal to p by q, then
Hmm. Hmm.
the then in our Rn
Hmm.
that x to the power m minus 1
Hmm.
will be of the form p to the power m minus 1 divided by q to the power m minus 1,
Hmm.
and and if we take like we are taking the LCM from our previous examples
Hmm.
in such a way that
Hmm.
this uh, we are taking that maximum power of q. So here like the LCM, if we take m q to the power m minus 1,
Hmm.
then we can just like then we can just make every other term
Hmm.
in terms of some integer divided by q to the power m minus 1, because their denominators are the lesser power of q. So that is we can take
Yes,
it
yes,
as
yes, correct, correct. Yeah, and further, can you tell me what is a naught value in this expression?
yes sir. Oh, a naught, okay, so a naught value is it is that the first term, that x to the power m,
So yeah, in this particular example, it is. Can you go a little up? Here you can see, right?
Yeah. So that is a x to the power m and plus minus a to the power m. So this two.
Yeah. Okay.
Because it's a integer too.
Yeah. Okay. So that is the last constant term is integer playing a role here to get. That is number one. And also you can see the pattern when first root 2, 2 power 1 by 2, we have by q. 2 power 1 by 3, we have q square. Yeah. But here we can observe the pattern much more better way. Okay. Very good. Thanks, Artis. Aridas.
Now, again, you can replace this two with any integers because you already have seen we have done the square root of n. So if you know about this proof, you can replace 2 by n and the same proof for. So what we will get is n raised to power 1 by n is if is not an integer, then it is irrational. Okay, so that's a nice generalization till now. But we have one more thing that we can do here, and that's what I like the most about this part. Aarti Das, do you have any question?
No, he raised earlier, I think. He not. Yeah, you can go ahead.
Okay, now look at all these numbers. So that's why I written x in this term. That's why I written taken x this number, because now you will see that n raised to power 1 by m can be seen as the root of x raised to power m minus n is equal to 0. So this number is nothing but the root of this number. It's a root of this. So if it is a root of this number, so next question is very obvious. Can we extend these results to the polynomials? And because it's a monic polynomial with integer coefficients, so the next question we can ask, if we have a monic polynomial, suppose of the form x raised to power m plus,
Krishan,
yes, sir. Yes, sir.
instead of 0, like it is like 0, we can put a box
Oh,
so that
sorry.
it will be clear. Yeah,
Yeah,
box, yeah, right.
worth 1.
Mhm.
X raised to power m minus 1 plus up to a1x plus a naught equal to 0. Suppose we have this polynomial and we are taking monic polynomial with one coefficient with integer coefficients. All those AIs are integers. Okay, so that is the proof. That's very easy. All you have to see that x raised to power m is nothing but the minus a m minus 1 x raised to power m minus 1, and if you go on minus up to minus a1x minus a naught. So that's the value of x raised to power m. And again, you take a is the greatest integer of x, and then you consider the number r, which is r1, also r x minus a, r2, which is x minus a whole square. Okay, and if you continuing on this, when you reach at Rn, x minus a raised to power m, that the first term will come x raised to power m, and you will put this value here. Okay, this value you will put instead of x raised to power m. So what we will get is every number Rn is of the form. What form? We have, I'm taking a capital A, I can use a of m comma n. There are two variables m and n, so that's why I'm using this. So a m minus 1 comma n x raised to power m minus 1 plus में a m minus 2 comma n x raised to power m minus 2 and so on. Plus में a1 x plus में sorry a1 comma n and a0 comma n. So again, you will see that all the numbers are of this form. So if you assume x is rational, then x is equal to p by q, and you can apply the same thing. So what we have is the result that if monic polynomial, if roots of monic polynomial with integer coefficients are not integer, then they are irrational. Now that's the last result I want to say, and that's if you, with the help of this, you can prove the golden ratio, which is the root of the polynomial x square minus x minus 1 is equal to 0. You all know, if you know, I don't know, it's not an integer, then it's an irrational number. So that's the way to prove. There are other proofs also that golden ratio is irrational, but I like this one, that it's a root of a monic polynomial with integer coefficients, and it's not an integer. So therefore, it is irrational. So I hope I will be able to deliver my point, the aim, that why this proof is important, because in this proof you see we extended it very nicely. So firstly, we get the extensions very nicely, and second point is this proof, for this proof you don't need prime numbers, factors, and all other things. So that's the aim I hope will be delivered to you. So if you find some other proof for the theorems which is well established, remember that there is always a different perspective you get, and it will be useful in some other ways. So you can also study different proofs of the same theorems. Thank you. I want to conclude here. So if anyone have any doubt, they can ask. Sir,
Jacob, yeah.
Yeah, sir. Uh, yeah. Hello.
Yeah.
Yeah. Is there any doubt, students? If you want to ask. Sir, listen, sir. May you please give some references for this reference book? I mean, am I audible?
You are muted, Krishan. Krishan, you are muted.
yeah, I found this on a YouTube video also, and there is also a book regarding this. So I don't have the right now, link and the book. Whenever I will share in the group. So right now I'm not able to do that.
Okay,
So
so if
you
you
can
do not,
search on my YouTube that calculus proof. That's the same what I explained here, and then I studied it in a book. Uh, I don't remember because I did it recently. So that's where I found it.
Okay. Are there any other comments you want to make? Any one of you? If there are no doubts, you can ask or say that your feeling about the proof or your experience in this talk. If anyone want to share. Okay. Okay, thank you for all of you for attending this talk. Make it convenient to attend this. Yeah, so I request that all of you please attend. We will update you whenever there is a talk. Also, I request all of you, you yourself come forward to give some talks whenever we are always be there to record your video. So also we'll discuss before the talk also. What is the topic you need to take up and all. Okay, thank you for attending.